Okay, let's get started. So we're continuing our discussion on analyzing non-symmetrical systems, and we talked about in the last class the concept of grounding, right? And again, that's a very important topic because grounding of systems is going to determine how much ground fault current you have, and will also determine the amount of damage your system can receive. So if you can, you would try to insert some sort of a ground impedance to limit the ground fault. Keep in mind that also can raise the voltages on the unfaulted phases, right? Because if you have a phase to ground fault and you don't remove that phase to ground fault for an extended period of time because you have very little current flow, then the phase to neutral is going to be much, much higher because neutral now is at the same potential as one of the phases. So some of the protection schemes you have to look at is how much voltage or how high will the voltage be on the other phases before damage will occur, okay? So generally you try to limit them to fairly short time. I will say when you do protection system design, you almost always set it as low as practical. And that's kind of a misnomer because every time I've seen it, arbitrarily set it to 1 amp secondary pickup and have a short time delay to coordinate with other elements. So it's pretty arbitrary for ground fault. There hasn't been a lot of research or discussion done, but it's something that we can talk more about if you take Power 3. So anyway, we're going to assume that the system is perfectly balanced everywhere else except the point at the fault or where the fault occurs. If you do not do that, then symmetrical components, you can't employ that. That only works for a single fault, and we'll see that in a minute. Most common one we talked a little bit about, that's the single line to ground fault. But we do need to analyze line to line and double line to ground. Even though the worst case fault current is almost always going to be the 3-phase, there are a few systems and a few times when I've actually seen single line to ground fault that has a higher magnitude than a 3-phase fault. Not often, but on occasion. So if those are the two worst faults, why do you think we would actually have to look at line to line and double line to ground faults? If they have less fault current, and we've set our protection elements for 3-phase and single line to ground, why would we look at those other two?
If they are less?
If they're less, they are going to be less for sure. Why would we look at them? When I think of fault currents, right, what do you typically think of? Got a 3-phase fault or a single line to ground fault? I got to respond to that, right? And I got to protect my equipment from those big fault currents. But there's also a concept of what's called reach. What if the fault is not one of those two faults, but it is a line to line or double line to ground fault? I want to be able to detect those faults and take them out of service or take them offline. So there are some instances when you actually set some of your protection elements based on minimum fault current levels because you want to make sure you see you have the ability for your protection to actually see the fault, okay? So you actually have to do these other cases so that you can see minimum fault currents and then still be able to respond and trip those, okay? Not super common, but common enough that I've actually had to do that, all right? So something to think about when you do that. And then plus the other thing is it's not that much more effort to look at the other two faults, so we'll include them anyway. I talked about the easiest method if they are perfectly balanced. So we live in a world, right, where I can tell you how to get from point A to point B in 3 dimensions by telling you an X and a Y and a Z. And do you remember from your 258 days the concept of a basis function? Maybe? Right? A basis function is essentially any vector, if you will, that no matter what you do to any other vectors, you can't recreate it, okay? So in Cartesian coordinates, we have 3 basis vectors in 3D, right? We have a unit 1 in the x direction, a unit in the y, and the unit in the z. So the idea of symmetrical components is to basically decompose those non-symmetrical or asymmetrical waveforms into symmetrical not balanced, but symmetrical elements. All right? So we need 3 of them, because if we have a possibility of 3 vectors, A, B, C, that are unbalanced, we need to break those down into 3 symmetrical ones. We've already been looking at positive sequence, right? Remember how I talked about early in the semester? We said ABC rotation, okay? That is positive sequence. And that's just the way that we've come up with a convention to say ABC. So this is positive or ABC rotation, right? The other one that we discussed briefly, but we didn't spend too much time, is ACB, right? Rotation. This is also called negative sequence rotation. Why do you think it's called negative? Normally we rotate this way, right? And we see ABC. What if we take the negative of the rotation? Do we still say ABC? No, if you operate in the opposite direction, you see A, then B, then C, right? So if you rotate ACB rotation in the negative direction, you end up with ABC rotation. Does that make sense? So you're just swapping them around. So this is called negative sequence rotation, because to get that ABC again, we have to operate the vectors in the opposite direction. And this is actually what happens when you do the math out. They have to operate in the opposite direction. The sine waves are operating in the opposite direction to get their response. So this is one that we'll append to. What do you think 0 sequence is? 0 sequence is a little bit different because we only have the 2 rotations, right? We have ABC or ACB. We can't have BAC. That's just an extension of either of ACB, right? So in 0 sequence, what we have is we have A and B and C, and I didn't draw those perfect, but they're all the exact same magnitude, just like the other ones are. In ABC or ACB rotation, these were all spaced 120 degrees. In 0 sequence land, there is no spacing. They all have exactly the same angle. That's why this is called symmetrical components, not balanced components, right? Because the concept of a balance is same magnitude, phase shifted by 120 degrees. In 0 sequence land, we don't have any 120 degree phase shift. And that will hopefully become evident when we start looking at ground.
So what is that single phase, I guess?
No, it's all 3-phase systems. We just have 3 separate 0 sequence components, A, B, C, that all have the same magnitude and angle.
Where would you have that in the real world?
When anytime you have current flowing through ground, which most grounded systems have some 0 sequence component. Okay? Here's positive, right? We have A. If we look at A first, we see with our rotation in the typical direction, right? Counterclockwise, we see A, then B comes along, and then C. All the same magnitude and phase shifted by 120 degrees. If I run A, B, C, positive sequence, how much current do I have going into the ground here? 0, yeah, because they're going to sum together, right? If 1 at an angle of 0 plus 1 at an angle of 120 plus 1 at an angle of minus 120 is your result, that should be 0, right? So in any balanced system, the sum of the currents at any neutral point or connection point have to be 0. So if I look at this ground here, does that matter that there's a connection to ground or not? Yeah. How much current goes here if the sum is 0? 0, right? So guess what? Whether this exists or not doesn't matter. It does not care to a positive sequence system if you have a neutral connection or not, because it sums to 0. all right? So here's a key thing, and this is if you're taking notes and you try to pay attention, you should highlight positive sequence networks. You couldn't care less how the system is grounded. Does not matter to you in any way, shape, or form. It's irrelevant. You can neglect or ignore the fact that there is a ground there because it doesn't care. It doesn't matter. All right?
As long as it's balanced.
It has to be balanced. We just said that we're going to decompose a set of unbalanced ABC, right? So in the real world, we have ABC that aren't balanced. We're going to decompose those into two perfectly balanced ones, positive and negative sequence, and one symmetrical one that all have the same magnitude and angle. So positive sequence absolutely 100% must be balanced. 100% has to be balanced. Okay?
Don't you want that ground now for protection reasons?
Well, I do want it for separate reasons, but what I'm saying is from the positive sequence perspective, it doesn't care. Couldn't care less. Maybe for a different reason, but from a positive sequence perspective, it has nothing to do with it. Here's negative sequence. Kind of looks like positive sequence. You just swapped B and C. So that if we were to rotate it in this direction, right? Rotate it in the opposite direction, we're going to see A, then B, then C, right? So that's why we call it negative sequence, because the rotation is in the negative direction. Now here's the thing. Are the magnitudes the same? Sure are. Are the angles spaced by 120 degrees? Absolutely. So in negative sequence land, do I care what's going on in the neutral? Couldn't care less. So for positive or negative sequence symmetrical components, they are perfectly balanced. Okay? And whether you have a neutral connection or not is irrelevant to you. Okay? Now that does not mean, just to clarify, if you have positive and negative sequence currents together, okay, they're individually taking at each other saying, you know what, we're going to have some ground, we're not going to care what the grounds are. But if you have positive and negative sequence representing your original phasors, right, your original ABC, that means that your system is not balanced, right? So one of the things, and we're jumping ahead a little bit into the next class, but one of the things you can do to detect that a system is unbalanced, you don't actually look at phase A and see that it's 1,000 amps, phase B and see that it's 800 amps, and phase C and see it's 1,200 amps. That doesn't matter. You don't look at the magnitudes. You just look at that guy. What is a negative sequence current? Because if we're assuming ABC rotation, positive sequence rotation, that value can be what it needs to be because that's based on load. If you have any negative sequence current, that would tell you, hey, the system's unbalanced. And some systems you expect it to be unbalanced, like distribution circuits, right? We're out of luck. We're going to try to do as much as we can to balance the load on distribution circuits, but a mirror or Avangrid is not going to send a team of workers out to kind of reconfigure some of the loads once it's set up. I mean, that's just, they're going to try to add additional load to balance it out, but they don't go back and fix it. Maybe they do periodically, but I don't know anybody who's ever done that, and I haven't, asked that specific question to the utilities. But as far to the best of my knowledge, that's never done. But from a generator perspective, Maine Independent Station's got 3 generators cranking out megawatts, right? What if those are getting negative sequence elements? That would tell me that there's a problem either with the generator or with the system. Most likely going to be the generator, right? Because the system's got thousands and thousands of generators and loads, and it's going to be pretty closely balanced at that transmission level. Not perfect, but pretty close. So if you have excessive negative sequence elements in your currents from your generator, that probably tells you that you've got an issue with your generator. So trip. So one of the elements that you set for certain protection elements, particularly for generator, is called a 46 function. These are, and this is important for those of you who are going to go working in the relay world, these are ANSI device numbers. You can look them up. There's a standard set of ANSI device numbers, Because you and I, we know what the letter A is and B and C. And, you know, we have a common nomenclature. We know what the number 1, 2, and 3 is. What if I have a generator here that's represented by a single line diagram? I've got a breaker, and over here I've got a CT that's going to a multifunction relay, and it's issuing a trip command to that breaker. What functions would be set in there? Set in the multifunction relay. You could actually call it out, say unbalance, volts per hertz, backup distance. Help me out, Briar. You did a lot of this stuff. Over or under excitation, so that's a 27/59. Hey, wait a minute. You just said 2759. What are you talking about? Should be over/under excitation, right? Well, it just gets to be a lot to write all these words down. So people have said an unbalance is ANSI device number 46. Volts per hertz is, I don't think it's 40. That's breaker ground. Volts per hertz is, come on, close. 24 device, right? So you literally can look it up and just say, if I look at a one-line diagram and it says a 46, then I just use my ANSI device number and it just says that's unbalanced. So what's actually configured in this fancy relay, and some of these relays, these multi-function relays, these generator ones, you know, 9, 10 grand, so, you know, fairly inexpensive, that actually has been configured to monitor for an unbalanced condition. And if that unbalanced condition is too high, you could issue an alarm, and or you can do a trip. Sometimes you have multiple levels, and you can do that all. So you use negative sequence for unbalance. It works beautifully, and it can be set very sensitively because the negative sequence should be 0. If it goes up to 10% or, you know, some non-zero value, and you can't set it too low, right? Because there's always going to be some unbalance. But you can't set it too low because there's also some inaccuracies with all this measuring stuff. You could say, oh boy, I got a problem here. So remember what I talked about when you have polarizing quantities or operating quantities in relays? You can actually specify positive, negative, and 0 sequence to trip. Because instead of looking at the actual phase quantities, which could be really high, you can look at negative or 0 sequence, which are calculated from those phase quantities, right? The relays themselves are just looking at phase current A, phase current B, and phase current C. And then it runs through some calculation to give me positive, negative, and 0 sequence. That's a very important nugget for those of you who are going to be working, and I know a few of you are, working in the relay protection settings, why these terms are important, understanding the concept behind there. Because, you know, a lot of people say, well, why bother teaching it? Because, you know, SIME, Aspen, all these programs, they don't actually use 0, positive, or negative sequence networks, but all the relays do. And that's what the protection is going to be for the foreseeable future based on these quantities. I don't see any change afoot to go away from that. Dan, did you have a question? Or?
I answered it myself. I was wondering if these are the same as the IEEE device numbers.
Yes. So just good question. So are these the same as the IEEE device numbers? So yes, be careful. Not be careful, but just as an FYI, ANSI is the American National Standards Institute. They vote on approving these standards to be American national standards, but they're all just copied from IEEE, ASME, you know, all these different organizations who actually have expertise in those areas. And not to say ANSI are a bunch of people who don't know what they're talking about, but IEEE is going to know a lot more about device numbers than ANSI would. And so then there'll be a balloting process to say, IEEE blah, 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 we balloted and it approved it to become an ANSI thing. So that kind of gives it one level higher of recognition, if you will. But whether you call it IEEE or ANSI device number, it's just been called ANSI device number for many, many years. You know, that's kind of the reason why. And just the one side point about IEEE, that's always a good thing to hang your hat when you're designing systems and you've designed it in accordance with IEEE standard, blah, blah, blah. If something fails and you get sued, you can say, well, IEEE blah, blah, blah was in effect, and I referenced it, and I actually designed it. See this specific paragraph where I highlighted here? That's how my design's based on. If you have to go to court, immediately the judge or the jury will be like, you know, this is an accepted industry practice that this individual followed. You know, it's not his fault or her fault. I mean, it's just, you know, that's kind of a way to hang your hat. And that happened to me a year ago. I got an email from somebody from a company. I did a generator protection setting, and he said, why didn't you enable, I think it was over frequency on this generator protection? You know, kind of accusatory email, although it's kind of hard to tell with the tone. And I just said, ANSI IEEE XYZ does not recommend it for hydro facilities. And I actually copied the paragraph. I put it in the email. I copied it. It said, per IEEE blah, blah, blah. And here's the excerpt that I used. Emailed it to him, and he never emailed me back. He just said, oh, okay, well, I'm obviously, you know, he didn't argue with the IEEE, even though he was the customer who said, you should have put that on there. It was on there before. Why didn't you put it on there? I said, well, IEEE suggests that it not be done. And just because it was there before doesn't make it right. And again, it just makes it very easy when you can just kind of put your hand up and say, here's that, and then everybody just sort of backs off. It just takes, you know, it takes the pressure off you. So I was fortunate that I had actually studied that to make sure I was good. So that's why when we talk about continuous improvement, you know, I'm 49 and I've been doing this since 1992. I still have to pull IEEE standards out. You know, I still have to look at those things. And you all are very fortunate because you can go to the library and actually access all the IEEE standards for free. You're not supposed to use them for commercial uses? What's that? Yeah, if you're on campus and you're logged into Tempest or UMaine Guest, you can just go to the library and it automatically logs you in and you can access any of the IEEE standards. If you're off campus and you're just studying for an exam, you can use your Main Street ID and log in, and then you can access it. Again, it's for educational purposes only, but I'll do a lot more of those next semester if you take Power 3. Okay? So, zero sequence, that is the zero sequence where they're all the same magnitude and phase. Notice they are equal to each other. So I'm setting you up a little bit. How about here? What happens to the neutral? Well, all the currents we'll assume are going in that direction. So my neutral current is IA0 plus IB0 plus IC0. Does that equal 0? If they're the same magnitude and angle? 1 at an angle of 0 plus 1 at an angle of 0 plus 1 at an angle of 0. Does that equal 0? To me, that equals 3. Right? So guess what? The neutral connection here on zero sequence networks is very important. That makes a huge deal. And so that's what the comment was earlier about, isn't it important? Absolutely, for zero sequence, which, guess what? I keep saying guess what because my dad does that, so I'll try to stop doing that. What's the current flowing through here? It's IN. What is the actual zero sequence current? It's 3 times A0, right? Because they're all the same. So when you look at these operate or polarizing quantities inside of a relay, it actually says I0. But it actually says 3I0. So you actually monitor 3 times the zero sequence current because you should have always the same magnitude, but times 3. So I've never seen I0. I've always seen 3 times I0. Okay? And just to confuse you, in Schweizerland, okay, or let's do generically, 0, 1, 2, positive, negative, and 0, right? In Schweizerland, they don't call it 0, 1, 2. They call it positive, which would be 1. What would be negative? Q. So if you look at the relay manual, their negative sequence values, sometimes they'll actually say 2, but if it says a Q in there, that's a negative sequence element, and it has to do with, if you remember back, we talked a little bit about how do you transfer a set of non-rotating phasors to rotating. You use ODQ. This is direct and quadrature access. So if I was to say, you know what, 0, 1, 2 is the normal sequence that we go, right? 0, then 1, then 2. Why did they pick quadrature? I'm guessing just because it lined up with ODQ, but I don't know that for a fact. I've never seen it confirmed. I just think that they did that just to make it, you know what, most people realize it's ODQ, even though most of you all will never do ODQ components through Parkes transformation, but you get the idea. And there you go. Sum the sequences, and clearly, if you look at my original phasors, EA, EB, and C, are those balanced? Do they look like their magnitudes are the same and their angles are 120 degrees apart? Not even close, in my opinion. If I was to strip that out, here's EA, here's EC, and here's EB. Does that look like a balanced set of phasors? But if I look at this one here, and I'll try to do colors, this one, and this one, don't those look like they're perfectly balanced? And if I go to my next, which is this one, and this one. So let's try to do them this way. Just kind of redrawing them as best as I can. Don't those look like they're balanced? Right? They're the same, they're symmetric. And then this one, and this one. Don't they all look like the same magnitude and the same phase? So I rebuilt my asymmetrical ABC into a set of symmetrical components, and they're all balanced. Now again, we go back to looking at per unit, right? Per unit is a lot of work, but it makes our lives so much easier doing all this analysis. It's the same thing here. When we have unbalanced systems, we can certainly look at monitoring the magnitudes, but how much ground fault current do I have? This doesn't help me with that. I'd actually have to be monitoring the ground. That's a great question. Do I actually have to monitor the ground to tell them what the ground fault current is? Do I have to monitor the ground to tell what the ground fault current is? No way, Jose. If I monitor the 3 lines and I put a donut CT around all of them, that's going to calculate the 3 magnetic fields going through there, right? And the sum of those, right, if they're perfectly balanced on 120 degrees, should be 0. If they are not, then they are not. So back in the day, you actually, to monitor 0 sequence current, and you didn't have a ground available, you actually just put a big window CT around all 3 phases, and that's actually how you measured ground current. Now, what they do is they just put a CT on each phase, and these are Y connected, grounded, the CTs, and then inside the relay, it takes the ABC and spits out 0, 1, and 2. It just does the math. It does literally linear algebra to calculate what the negative sequence is. So you don't have to do those donut CTs anymore. You just measure that. So all the newer stuff that you've seen in the last probably 5 or 10 years, you don't see overall window CTs anymore because you can just get the same result, right? You just do it mathematically. Okay? Am I boring you getting off on all these side things? Because I'm trying to set you up for interest in the future. And I know a lot of people, I mean, if you're going to be working in the test arena, like some of you people may perhaps be doing it, understanding these symmetrical components and what's happening, because the actual test equipment that you have can actually inject phase currents based on, I need a negative sequence component of this. I need a 0 sequence component of that, because that's actually what you've set for pickup values, which are those actual values. So you have to understand, why am I setting this negative sequence value to this, and then the phase currents are coming out. That's typically, or that's kind of an important activity that you need to do. What's that? Thinking of donuts? Well, I should have brought some. Sorry. Okay, any questions on the positive, negative, and zero sequence concepts? It's super incredibly important. Again, if there's a couple topics that you're going to pick up from this semester, number one is per unit. That's the most important topic. And doing symmetrical components and understanding what that means is probably number two, if you're going to work in this utility industry. If you're going to design, 50,000 amp power, 50,000 watt amplifiers, that might not be so important to you. But if you're going to work on the utility system, even working at a paper mill, it's important because all the newer stuff coming in, and these paper mills have to replace equipment, and so how do you set them? So if it's all molded case circuit breakers with trip units, all you're monitoring is phase currents. But if you're going to get to the next level of sophistication, you're trying to protect a 1,000 horsepower motor, maybe calculating unbalance is a very important quantity to you. Okay? So it might not be as important if you're working at a paper mill, but all the concepts apply, whether it's 480 volt distribution or 48,000 volt, 480,000 volt, it's all relevant. Okay, any questions? All right, well, let's simplify our work because we know that we can rebuild our currents or voltages. This applies for voltages too, right? Currents or voltages, it works either way. You will note that there is not positive, negative, and zero sequence power. There is only power on phase A, power on B, and power on C. Okay? You actually can do Z012, but most people don't actually do that because, again, are you monitoring actual impedances? No, you're looking at currents and voltages. You might actually calculate what the impedance is going to be based on either positive or negative or zero sequence elements, but you actually don't calculate, specifically what Z0 is. You would just basically say that's the ground impedance. Yes, sir? It would be what the ground impedance is seen because you have a ground fault. And ground faults are the absolute worst, most difficult to protect against. So getting off on a side topic, if I have a three-phase system with one of these grounded, so normally if you have a system that you're trying to protect, sort of at a distance, you can look literally at the impedance. What is Z? Is Z within a window or outside a window? If it's inside this window, so if Z is in here, trip. If it's outside, no trip, right? Ground fault is so bad for using that you don't just rely on this 21 element, which is called is it an impedance element? It's actually a distance element because how far you are away from a fault, right? So I'm a relay here sitting here monitoring for a fault. The impedance of the system changes as the fault occurs, right? When you see a load, there's a V divided by I, right? I get an impedance. If the fault occurs, it's going to shorten the impedance, right? So the fault is actually closer to you. That's why they call it 21, which is actually looking at impedance. They don't call it an impedance relay, they call it a distance relay. But there's a phase and a ground, and the 21G is so bad that there always has to be a backup. Why do you think it's so bad? Well, that's the same thing for a phase. Why would a ground be so bad? Because if it's a phase, right, it's probably going to be a line-to-line or a three-phase fault. So you have a really good return path, don't you? Your impedance is going to be not really changed because of the return path because of that. What about the ground? It's always changing. It could be here. You have a wire that's touching the ground. It's arcing. So you could have a pretty high impedance there. So the distance element for ground is not great because of that fact. So every time I've set a 21G, I've always set a 67N. How about for homework, you tell me what a 67N function is? Is that a good little test? People looking at their phones saying, can I submit it now? So that's one of the things you can look at for distance. So every time you see 21G, you'll always see a 67N. At least every time I've seen it, because it's not reliable enough to actually work. So, and one of the things you do is you actually look at faults, and you actually have a ground that actually has a wider path. So remember how I said it's a circle? In ground, many times, I've actually seen it as a rectangle, because the ground fault, the ground impedance can be so high that you can get some wonky results. We'll talk about, if you're interested, we'll talk about distance elements and all these shapes. You know, one's a circle and one's a rectangle. They're actually called a mole characteristic, and the other one's called a quadrilateral characteristic. So, but we'll talk about that if you take the following class. Actually, somebody here in the back can actually talk about that already if she wants to, or she probably may not remember.
No, I remember. You can basically graph the area with which you're going to monitor. And so, like you say, they can look different depending on what you're looking at. But just determining where the fault is, whether or not it's in front of you or behind you or what's going on, is the relay's job.
Yes.
And they use these convenient graphs to determine what kind of range you can expect for it to be okay, and then where you're going to expect for there to be something wrong.
So the relay specifies the circle or the box, but guess who actually specifies the circle or the box? The engineer. Yeah, the engineer picks the characteristic, and guess what else the engineer does? Picks the size of the box or the circle. And is it skewed? Is it offset? Does it look in the reverse direction? Do we have to do something called, I'm going to say this incorrectly, let me think of the term, load encroachment? All right? We don't want to trip on load, do we? But how does the relay know if it's a fault or a load? Just based on the impedance you picked. Can't be just current, because it's voltage dependent as well. So it actually needs to know those characteristics to be able to determine that, and you have to set all those. Plus the delays associated with it. Do you reclose? Do you not reclose instantaneously? I can get into all kinds of things, but I will bore you. Yes, exactly. So POTT. So he's bringing up a comment about what is POTT. That's permissive overreaching transfer trip, and it's just a high-speed communications signal that actually speeds up or blocks the operation of your tripping scheme. So no, it does use distance elements, but it's based on trying to speed it up or slow it down. There's POTT, PUTT, DCB, DCUB, DTT. Briar, am I missing any? Briar's like, what are you talking about? And those things used to be really easy because they would use, they would lease telephone lines. Can you lease telephone lines anymore? You had to have a dedicated copper line, so utilities used to get dedicated copper lines that would actually send these signals over the telephone wires. You don't want to necessarily, well, there's a bunch of different ways you can do it, but you want a pretty reliable one, so just run it over a telephone wire. You think the telephone company is going to reserve a copper pair of wire just for little old you? You know how many phone calls that thing can take with data and all that stuff? So it's getting harder and harder to get a reserved line. They're just like, no, we need it for yourself. So that's why you'll see the OPGW, the overhead ground wire that actually has fiber in it. Also, sometimes you use power line carrier, which you actually use the conductor, the transmission line itself to emit it. In Amera territory, they use a lot of power line carrier that's, not power line carrier, they use microwave. So if you see a tower and another tower, that's how you do microwave transmission, but it's going to be perfectly line of sight. So each one of those has downsides, but ground wire is probably going to take over. In Connecticut, they're replacing all their ground wire with OPGW because it's so much cheaper and efficient, and you can transfer massive amounts of data. Once you have fiber, what's the data transfer rates on a fiber? Yeah, gigs and gigs of data. And it's secure, right? How's a bad guy going to get into interfere with a fiber optic line? You got to have light. and they have to splice into it. You think you're going to have a bad guy splice into an overhead ground wire over a 345 line? Good luck, right? Not going to happen.
Make a drone for that.
They could probably make a drone, but yeah, I mean, that'd be a pretty fancy drone that can cut into a wire and do all that stuff, so good luck with that. So we're going to add those add the 3 individual components per phase. So to rebuild the phase A component, we just add phase A 0 sequence, phase A positive sequence, phase A negative sequence. We do the same thing for B, and we have the same thing for C. Which is all well and good, but aren't these all the same? Aren't they the same magnitude and angle? So why do I need to call this IB0? Why don't I just call this AI0? Pardon?
Those parts of the vectors might not be the same.
No, they are the same. They have to be the same, right? That's the whole thing. So why not call this IA0?
Might as well.
Sure. And do you remember negative sequence IB? Here's A negative. Where does IB live? Up here, right? So isn't IB negative equal to IA negative? They have the same magnitude, except it's phase shifted by 120 degrees. So I can replace this with IA negative, but I need to multiply it by 120 degrees. 1 at an angle of 120. I don't want to write 1 at an angle of 120 every time. I'm lazy. So I'm going to come up with a brand new variable called A. A is just a phase shifter. So A is equal to 1 at an angle of 120. What does A squared equal? Well, if I take complex numbers, right, and multiply them, I multiply the magnitudes and add the angles. Isn't that 1 at an angle of 240? Which, as Dan correctly pointed out, is the same thing as 1 at an angle of minus 120, isn't it? It's the same thing. So I can use that fact, and instead of writing my ABC as the sum of all those elements, I'm just going to solve for 3 elements and multiply it by this fancy matrix. And that's how I rebuild my matrix. Okay? So why is this good? Because I have 3 equations and 3 unknowns. So remember how I told you the relay is monitoring ABC current? I can calculate the symmetrical components as long as I have 3 currents to measure. I know what this matrix is here.
It's not going to change, right?
And it does not change. That's fixed. Then I can get all the symmetrical components. If I had to go B and C, that would be a lot of work. I'd have 9 different values, but I actually don't. I only have 3 values, right? And 2 of them just happen to be phase shifted to get the B and the C. So let's just go and build 3, because I actually have additional information. Dan?
So that answer is going to be our 3 line currents. I guess we just would add them up, or whatever to see if it's balanced or imbalanced.
Say that again?
That our answer is going to be our 3 different line currents.
No, the answer is not going to be the 3 different line currents. Remember, we're in the real world. We have the line currents, A, B, and C. The relay is not necessarily operating on A, B, C. It might be operating on positive, negative, or 0 sequence components. So the relay will actually convert those into those components, and then it will operate on these. So most of the time, you actually have these. You need to check and calculate these. Now, if you're designing a system, right, and you're trying to set the protection elements up, I don't know. The relay is going to have the phase currents, but you have to set the elements to trip based on certain parameters. So when you do your upfront analysis to figure out when do I trip, when do I not trip, you actually have to do all the calculations to solve for these. Okay? So when you do your initial setup you need to be able to calculate what the phase currents are going to be. So like you can design your breakers or your system to handle those fault currents, but it's all going to be based on coming up with a way to calculate your symmetrical components. Okay? Make sense? Put this in your calculator. A. Don't mess around. Put it in your calculator and save it as A. Put it in MATLAB, save it as A. You will do this a lot. Okay? You will do this a ton this semester. Don't mess around. Just specify it in there, and you won't have to worry about which direction, is it right, is it wrong, etc. All right? That's the A matrix, and that never changes. That's why we're going to enter it in. Do you want me to pause for 3 minutes so you can put in your calculators now? All right, I'll pause. Okay, so we know what the A matrix is, and that's never going to change. So if we want to go from symmetrical components, if we have the ability to determine what those are, which we'll be doing when we actually calculate fault currents, we can actually get phase currents from our symmetrical components, right? So real world currents we get from our symmetrical components. If we do a little bit of fancy-dancy math, right, multiply by the inverse of a matrix, we can actually go from phase currents to symmetrical components. And if you do your algebra, that's what the inverse of A is. You have multiply by 1/3, and then these two have swapped. That's the only difference. Why did I tell you to store the A matrix in there? Because your calculators can do A inverse, right? You don't have to store A inverse. It'll actually have the ability to do it for you. So again, this one is more important in some respect because once you actually have real-world quantities, that's actually how the relay interprets or gets positive, negative, and zero sequence currents. Okay? So all relays do all day long is they monitor voltages and currents, real-world voltages and currents. Some of them that are actually, doing the residual that are actually calculated on there, are on there, those are calculating 3 times I0, measuring 3 times I0. But all the new stuff doesn't need to do that anymore. Okay? So a lot has changed, but this now is way more important. So let's do an example. We have 3 actual phase currents, 10 at an angle of 0, 10 at an angle of minus 120, 10 at an angle of 120. I would like to calculate the symmetrical components. So this is my I matrix. This is my A matrix, or A inverse matrix, I should say. That is my symmetrical components matrix. Uh-oh, I made a mistake, didn't I? What happened to my zero sequence and my negative sequence? My positive sequence is there, but my positive sequence is there, but what happened to the zero and negative sequence?
They don't exist as a positive sequence.
Pardon?
Is it just because it's a positive sequence system?
No, it's a real-world ABC system. It has positive sequence rotation, or ABC rotation, I should say. But that doesn't mean it's a positive sequence system. It's just ABC rotation. So why is there only a positive sequence number? 10 at an angle of 0, 10 at an angle of minus 120, 10 at an angle of positive 120. Isn't that a perfectly balanced system? What's its rotation? ABC or positive sequence rotation. Shouldn't you only get a positive sequence set of numbers if it's a perfectly balanced ABC system? If you don't, then guess what? This work doesn't make sense. It's broken. So you get exactly what you expect to get. When you have a perfectly balanced ABC system, you should only get positive sequence rotation. Come on. Not impressed? This works? Yes?
In the calculator, you were out of the room, any variable could be used to represent the A matrix, right?
Yes, you can call it Susan, you can call it Briar.
And you don't have to specify
Yes.
Just want to make sure. I'm not misleading people.
Yep. Nope, you can call it whatever you want. What if you swapped, so over here, right, this is A, B, C. What if I swapped B and C? Now, this is B and this is C. What type of rotation is it experiencing? Is it perfectly balanced? So shouldn't I only get something in the negative sequence rotation land? Absolutely. If we did zero sequence, what would you measure? That's a much harder one, isn't it? Because you can have an unbalanced set of phasors and you can have no zero sequence current. Right? We already talked about having positive and negative could be enough. The zero sequence element is determined by the ground. So I actually need additional information. I need to know what the ground is. We'll get to that. Here's example number 2. 5 at an angle of 90, 8 at an angle of 150, 8 at an angle of minus 30. Is this a balanced system? Yes? Are they all the same magnitude? No, one's at 5 and the other two are 8, so it's close but not exactly. Do they all have 120 degrees of separation? 150 to 90? 150 to minus 30, is that? 90 to minus 30 is, but minus 30 to 150, that's not 120, and 90 to 150 is not. So if I want to calculate my symmetrical components, I have a 0, and a 1, and a 2. Those are not the same. Yep. Since I'm such a magnanimous person, I did the MATLAB script for you to do this problem. And I did it, tried to be consistent with how you might want to enter it in your matrix. I specified A using Euler's identity, right? 1 at an angle of 120, that's how you enter this into the calculator. My capital A matrix has 1s in the row, first row, then 1 A squared and A in the second row, and 1 and A squared in the third row, right? Then I specified my phase voltages, and I just specified a 3x1 vector. And again, I just entered those in as complex numbers, magnitude and angle. Then I calculated my symmetrical components by multiplying by A inverse times my phase voltage. And then I actually wanted to display my results to make it a little easier. So I did this vsim display. So this is 0, positive, and negative. Does that match the previous results? Pretty close, right? There's more precision in MATLAB than when I did this in the calculator, but it's pretty darn close. So you get 0, 1, 2. And just for fun, is that the original set of vectors that we have? 5 at an angle of 90, 8 at an angle of minus, what was it? Minus, I don't remember now, minus 120, 130? One was negative 30? Oh, well, actually, you know what I'm plotting here? I'm not plotting the original phases. I'm just plotting the symmetrical components. So I added this in here if you wanted to show you how to do the compass. Compass is basically doing a polar plot. So I actually plotted the zero sequence, negative sequence, and positive sequence, not the original vectors. I certainly could have. I certainly could have plotted, added them up and plotted it and gotten the original ones. Yep. You can put both on the same compass. The problem is sometimes it just gets a little hard to read because it's, again, a MATLAB works, but it doesn't make things super beautiful and easy to work with at all times. Question? So, use this if you want. Again, MATLAB is a fancy hammer. or a fancy screwdriver. You don't have to use it, right? But it just gives you the opportunity. And again, this keeps me honest. There's nothing up my sleeve because I did this as a published file, and I got the same results as I did in the slides, essentially. So remember, everybody's waiting, and sometimes it used to be in classes. People have given up on that, I think. But they used to sit there with calculators to see if I would make a typo. And I do. I make mistakes every once in a while and sit there and try to catch me. So this way, can't catch me in this one because I already put it up there on there so you can prove that. But if you want to run the script file, you can go ahead and type it in, see if it works. Okay? Are you happy that the script file is there or not? I mean, I don't have to put it up there. Yep. Just kind of silly, little simple one, but I wanted to also show you the compass thing. Here's another one, and I'm not going to show you this one. But I actually show you how to go from symmetrical components to phase components. Okay? So just going in either direction. Works perfectly fine. Yep. All right, so now we want to figure out our symmetrical components and how to use them. So we got to do a little bit of slogging to figure out, that whole neutral thing and all those impedances and how we can use them, right? Because what we'd like to do is work in symmetrical component land, if at all possible. Do our work because it's easier to do our work in balanced systems. Is it really easier to do our work in balanced systems? This is how we've done everything before, right? We've done single line or one phase analysis, haven't we? If we have three phases and they're not balanced, is this voltage to ground the same as this voltage? Or this voltage? They are not the same. So that whole approach about doing single phase analysis, wave bye-bye, because you can't do it anymore, right? So doing single phase analysis is much easier for us to do it on paper. So if we do symmetrical components, we can do everything as a single phase representation. If we're going to do things as an unbalanced system and keep track of everything, you can certainly do that. And that's what I said. That's what Aspen does. Well, I don't know that for a fact, but I'm fairly certain that's what Aspen does. A lot of that's proprietary, so I don't tell you anything. But Aspen, SIME, all these programs that can work in unbalanced systems, they just keep track of all three phases. They keep track of all the impedances in each phase and any mutual coupling between them, and then they go ahead and do the analysis that way. So they actually do the brute force approach, which is we're just going to calculate all three systems and go from there. That's why you spend $50,000 and you need, fancy infusion software to go ahead and schedule all these things, because you've got, when we talk about an 80,000 bus by 80,000 bus, Y bus, it's actually 240,000 by 240,000 because you're keeping track of all the phases. So inverting that matrix is not an easy thing. So let's go ahead and just build things from our phase components, right? So we have a neutral current, which is the sum of ABC. We have the ground current for phase A, going to be equal to whatever the current is in phase through the line, times that voltage drop, plus whatever voltage drop we get there, right? We're doing it relative to ground. We're just basically doing KVL to ground. And we do the same thing for B and C, and we can build that matrix based on that fact, right? ZY plus ZN is in the phase A, and then the other ones are just ZN, right? Because there's no B current going through phase A. It's all phase A current. So here's our matrix. Now let's convert everything over to symmetrical component lands. So we know what V equals Z times I. And if I want to convert symmetrical components for voltage to phase components, I use V equals AVS. Same thing for I. So now I'm going to substitute, this into here and this into here, right? Because those are equal. And then I end up with this. Now I'm going to solve for Vs. And I have that matrix. When I multiply A inverse ZA together, I end up with this. Wow, that's a pretty big deal. Anybody want to guess as to why? basically it's telling me V0, V1, V2 is going to be equal to Z plus 3Zn times I0, Zy times I1, and Zy times I2. Wow, that's a big deal. Does V2 give any care or consideration about what's happening in the positive sequence network or the zero sequence? And vice versa, right? So this is showing me that I've decoupled my networks. In a balanced system, the networks are completely and entirely decoupled from each other. So I can solve for positive sequence, I can solve for negative sequence, I can solve for zero sequence, and not even care what's happening to the other ones, right? So I have my symmetrical components. And I can draw my networks, right? I can show you how my zero sequence network, right, just looks like that. I don't have any positive or negative sequence elements there. Same thing for this guy and this guy. They're all independent. So I've decoupled. What's interesting, though, is that guy. It's not Zn. It's 3 times Zn. Why do you think that is? Because what flows through the neutral? All three zero sequence currents, which is the same, right? So the 3 comes from the fact that I've got 3 balanced currents flowing through there. And that's how that works out. So they are decoupled. Now, I've got my generators. So I'm going to draw my sequence network for my generators. Generators are the only one that put energy into the system. Agree? So if they're the only ones that put energy in the system, they're the only ones that should have a power supply in them, right? Motors actually can too, but usually only at faults. But these can actually put energy into the system. So I actually show a voltage source in there. Why don't I put one here and here? The comment is you can't have negative sequence in a generator. You can, but if you build a generator that puts out unbalanced voltages, is that a good generator? You want as perfectly balanced a system as possible. So you're buying a generator that is as perfectly balanced as possible as well. So balanced that you're only going to show that there's actual voltage coming out of the positive sequence, not in the negative sequence and not in the zero sequence. Okay? So the only energy in the system is from there. Now you might start to ask yourself, well, why bother drawing the negative and the zero sequence if there's no power? Well, we've talked a little bit about it. They're completely decoupled, except where? At the location of the fault. So where the fault occurs, you actually will tie those networks together, and then that energy source, that power supply, will actually cause current flows in the negative and zero sequence. It's induced at the point of the fault. Okay? So, you will note, and Breyer brought this up, why is the ground important? Because if you can have zero sequence current flowing, you had better have a ground. So that's why you put 3Zn. What if it's an ungrounded system? What does Zn equal? An ungrounded system is 0? That to me sounds like a short. That seems like a perfectly grounded system. Infinite. So what does 3 times infinity equal to? 3 infinity or infinity. So this is an open circuit, right? So the ground makes your determination for zero sequence there. Okay? Now I'm running out of time and I'm not going to try to do this one because this is the hardest one. Understanding the sequence networks for transformers is the hardest, most confusing, most difficult one that you'll come across by far. You're looking forward to the next class? We could go a little later now. There's some people in this room who've got a test in a few minutes with me, so we could torture them. But just think about this, okay? So I want everybody know what a mantra is? What's a mantra? What is it? Sort of. Motto. You'll let me explain? That's kind of you. A mantra is something that you say repeatedly, and it centers you, it helps you understand something, right? You know, like if you're really stressed out, you might have a mantra saying, I will remember to breathe. I will remember to breathe. And so it helps you center, it helps you remember something important about that moment. So with all the other craziness that's going on, you just go to your mantra and you can, kind of get yourself back into your conscious brain. Here's your mantra for sequence diagrams for zero sequence for transformers. What flows in the primary, flows in the secondary. What flows in the primary, flows in the secondary. Can we repeat that together so we'll have a mantra? What flows in the primary, flows in the secondary. And with that happy note, enjoy your mantra, and I'll see you on Thursday.